Welcome to Ex Terra Extra. I'm Tom Patton.
I'm Mike Turner.
And today we're going to talk with you a little bit about space power. Now, space power, Mike, is one of those things that when I was on a podcast with one of our guests who we'll hear from in a little bit, they said something along the lines of everything works better with power. And space is no different. Everything works better or requires power. And the other analogy that was made was that space is like a camping trip, and you only get to use what you take with you. If you don't have it with you when you launch, then you're out of luck.
That's true, because carrying that extension cord is a real bitch.
That's a long extension cord. But some of the things we're going to explore today really kind of go against that grain. That'll talk to you about how we can generate power in space, how we can use the power that's already available in space through a whole lot of different technologies. And Mike, it's just been a really interesting thing doing all this research and finding out how space power is critical to the future of space exploration. And that really is the essence of what we're going to discuss today.
Yep. Yeah, and you have to have power, whether it's a satellite, if you're going to do any kind of transmission or any kind of reception of whatever signal to you, which can be not just radio signals these days, but it can be laser.
Or also if you're going to get anywhere.
If you're going to get anywhere, there's more and more electric-based propulsion, life support systems. If we're talking about manned space flight, as we start doing more sophisticated and intensive things in space, we're going to require higher energy densities. And boy, if this starts to sound familiar, this is the EV argument. A high energy density of gasoline versus lower energy density of batteries, and of course that's the whole idea behind the lithium batteries, or lithium iron phosphate, or the lithium ion batteries, which is try to get the energy density higher and higher. And of course, I wonder if anybody is in the space business might have some knowledge on those kind of batteries, like SpaceX.
You think?
So there's a lot of linkage here to Earth and space, and it's really. It's going to be more and more critical as we need more and more, just as here on Earth, as we go into space, we need more and more power. And the traditional means of getting power has been solar. It's been the good old sun, and which is great if you're here on Earth or if you're near Earth, if you're on the moon, if you're going to Venus, Mercury, it's great. You got a lot of intense sunlight.
Lots of sun.
Lots of sun. But we go to Mars, and I believe, if I remember the number correctly, it's like 43% of the amount of energy that you get from Earth. Right. And you go out further, and the inverse square law in physics says the further out you go, everything drops by the square, and power just drops off pretty dramatically as you go further and further out. So we're going to need other ways of powering all of this wonderful stuff that we're going to do. And
there are some options that are being considered, and among them is nuclear. And the nuclear question is one of those things that nuclear got to be kind of a bad word, for lack of a better term. Everyone got really afraid of nuclear power after 3 Mile Island, after Chernobyl. Nuclear was one of those things that people started to back away from. But in space, nuclear is going to be one of those things that's going to be long-lasting and reliable and relatively safe.
Well, if you think about it, World War II, we had the dropping of the atomic bombs. Then in the 1950s, we had all those great cheesy B movies, B sci-fi movies about all the monsters and radiation. We had Dr. Strangelove and Failsafe and those good scary nuclear movies, and scared the bejesus out of all of us. And then we had the likes of 3 Mile Island and Chernobyl. I do not rank Fukushima that way. That wasn't a nuclear
that was a natural
accident.
disaster.
That was a truly natural disaster. Excuse me. And of course, the idea at the time was everything would, nuclear power is so powerful and so scary. But if you think about it, we spent all these billions of dollars creating nuclear weapons to be more efficient. All that fallout we worried about in the late 50s and early 60s. There's still fallout, but if your bomb is 90%, I don't know if it's there. I have no idea what efficiencies there are in nuclear weapons, but if it's 90% efficient, you only have 10% fallout, and back at, the Hiroshima, it's probably, if it was 2% efficient, everything else was just radioactive fallout. So, we had all kinds of ways to scare ourselves, and we've learned a lot in 3/4 of a century. But I think the biggest argument for nuclear power in space is, number one, you're in space. It's a high radiation environment. Get over it. You have to survive in that high radiation environment because you are staring down the barrel of a giant nuclear fusion reactor called the sun. And so you have high radiation. You've got a shield for that. So what's the big deal on having nuclear around? If you've got a shield from the sun, that's a lot worse than the nuclear that you've got a shield for. So suddenly nuclear power makes total and complete sense for space travel, except for maybe thermal issues. Right. And I'm no engineer, but the thermal issues are probably the biggest issues for any kind of nuclear use in space.
And of course, NASA is working on some nuclear proposals for things like habitation of the moon, the kind of small nuclear reactors that would be able to power lunar bases and then eventually Martian bases. It's called the Kilopower Project. Mm-hmm. And it really is, its weight ratio is such that it would be easy to get to one of those bodies and assemble and get going. It just really was one of those proposals that seems to make a lot of sense.
Well, again, it's does it need to be shielded? Yes, you have to protect people from it. But on the other hand, those people aren't going to be spending a lot of time on the surface because no matter what you put on the moon or on Mars, it has to be shielded from radiation. So, it's just like you have to take oxygen with you. You're going to have some shielding, and if you have the shielding, then nuclear is not such an issue anymore because the shielding is a necessity, just as food, water, air, and it's just makes a lot of sense. And if you're going to survive on the moon or Mars, a couple of the concepts are either put regolith over your space habitat, whatever that may be constructed out of. Mm-hmm. Could be blown up like a Sierra Space life habitat, or maybe a standalone metal type of system.
Or could even be dug out of the moon surface itself. Could be underground.
Could even be dug right out of the surface, yeah. But that's the point. If you're going to move rock, if you're going to cut into rock and move
you gotta have power.
You got to have power. You got to have a lot of power. But on the other hand, I thought one of the most interesting things was how much oxides there are on the moon. There's oxygen on the moon, mm-hmm. all over the place, but it's bound to a lot of the various minerals, particularly metals. And if you heat the metals up, for instance, they have titanium dioxide up there, right. Or titanium oxides. Titanium is a great metal used in aerospace. And so you're going to have to melt the regolith to get to refine the titanium out of it. When you do, your impurities are released, and one of those impurities happens to be oxygen. And well, lo and behold, I think that's kind of interesting. You could be generating your own oxygen as you're melting your way to casting your own habitat. But I don't know how the math works out. That may be a pipe dream, but maybe the math works out that way.
Well, it may be a pipe dream right now, but we've seen a lot of things that have been pipe dreams that have come to reality. Things like radio, television. Yes. How can I beam pictures across over the air? Well, guess what? Yeah. Anyway, coming a little bit closer to home in Earth orbit, there's also technology that's under development right now, which is the wireless energy transfer. Now, this is not really new. Tesla was working on, not Tesla the car company, but Nikola Tesla was working on wireless transmission of energy way back in the very late 1800s. But what this involves is beaming energy via microwaves or lasers, or even just as a light, from space-based solar power arrays to things that would need it. Now, there's a company that we talked to recently on the Ex Terra podcast. It's called Starcatcher. And I'm just going to let Andrew Rush, the CEO of Starcatcher, explain how that system works.
So the way our system works is we will build a constellation of what we call power node satellites that will collect a substantial amount of solar energy and then redirect portions of that energy to two client satellites. So one power node will service up to 50 or so client satellites simultaneously, and giving them the amount of power that they need, anywhere from a few hundred watts to dozens of kilowatts, at concentrations that vary from 1 sun to 5 or 10 suns of flux, again, based on their need. And what we're taking advantage of here are a couple of things. One is that solar arrays are they're photovoltaics, or what we call a band gap semiconductor. So if you send, and the way that these band gap semiconductors work is if you send, one photon within the wavelengths that to them within the wavelengths that they convert to electricity, it'll generate a certain amount of electricity. If you send 10 times that, it'll generate about 10 times that amount of power. And so that's how we're able to give folks additional power when they need it. And the rest of the power system, is comprised of a power processing unit and a battery. The battery is really collecting that energy and holding it for for operations, either high intensity operations, like operating a large synthetic aperture radar or a thruster, as well as operating when it's in eclipse. So we can give folks additional power when they, when they're operating, as well as just make sure that they're always, topped up, as it were.
Now, obviously, Mike, that's about powering satellites. And the way Andrew explained this to me is that the satellites don't need any kind of special receptor as long as they're within range of the power generating satellite. They just beam, and he used the analogy of a flashlight shining the power onto the existing solar arrays and charging up the batteries. Obviously, if you put something like that in an orbit around the moon, for instance, you might be able to power things on the lunar surface as well. So it's kind of really an interesting technology that they're working on. They're just really in the barest beginning stages of that, but it's a company that really, I think, bears watching.
Well, if you think about it, most any power system, there's two components. There's the power generation, and then how do you get the power from point A to point B?
Right. Generation and transmission.
Yeah, and so there's going to be a lot of technologies that are going to going to continue to be able to use solar power, because they don't need a lot of pardon me, they don't need a lot of density in energy or power, and there is a difference between the two, however, you do need to get it from point A to point B. And, I made the joke about there's always the old joke about the extension cable and the extension cord and all that. But in fact, how do you do that? On if you're on the night side of the moon or the Earth, you're obviously not going to get solar power. But if you do have a way of reflecting it or transmitting from satellites that or power generators that are either in sunlight or have power that they can transmit, you can continue to have power for any kind of object that is in the shadow of whatever celestial object you're dealing with. The other thing is when you do have to have some technologies, like I think it's going to be this way with tunneling and mining, you're going to have really high energy densities. That solar is probably not going to do it. Or if it is, I mean, you do have a lot of real estate. You can put a lot of solar cells, but but now you're talking about actually manufacturing them in situ, because if you don't, it's awfully expensive taking it up there.
Right.
That's where nuclear becomes more of an option.
One of the other things that's been talked about and that NASA, I know, is working on is regenerative fuel cells. These would recycle resources to generate power during dark periods. You mentioned the smelting of titanium on the lunar surface, mm-hmm. which generates oxygen, which could be part of a fuel cell closed circuit system. Those are the kinds of things that are going to be required for, I think, some of these long-term solutions, just because we're going to have to, in a lunar environment or in a Martian environment, have to use the resources that are available to the people that are there, because you can't lift everything to those bodies.
Well, that's true, but the titanium example there, you have oxygen, but you still need the hydrogen,
right? If
you're going to have the fuel cell. However, there are other compounds with hydrogen, and so as
water,
as we
for
get
instance.
into I'm talking about hydrogen compounds that are hydrogenated molecules, where it doesn't necessarily have to have oxygen within it. It's hydrogen chloride, hydrogen bromide, something like that. Once you strip that hydrogen off, it's got to go somewhere. And if you can pair it with the oxygen in a fuel cell, great, you're generating power. Not only that, but your waste product is water, and the water does a number of things for you. You can drink it, you can take a shower with it, you can water the plants with it. It can get rid of other waste for you, and you can split it up and create oxygen and hydrogen for other purposes. Oxygen, obviously, for breathing, hydrogen for other chemical purposes, and water also makes an excellent shield against radiation.
Think of that.
Or at least some forms of radiation.
Well,
it's a great neutron moderator.
The whole the whole concept of solar power has, of course, been around for a long time. And early in the space program, it was all about solar cells and batteries. Sputnik, for instance, had very simple batteries. Vanguard 1 was the first solar-powered satellite. That was back in 1958, the year I was born. And it's also been used in long-duration missions. And it's also been, you talk about things like solar sails, which has been in the realm of science fiction forever and is now finally coming around to something that is actually being used for propulsion in space. It's all powering deep space probes beyond the reach of what would be traditionally considered solar energy. Now, the power arrays on the International Space Station generate around 120 kilowatts of electricity. That is, to date, the largest space solar installation. But there are also some new advances in this technology, including multi-junction solar cells and their increased efficiency. And one of the companies that's working on that is a company called Redwire. We talked to them recently on the Ex Terra podcast as well. Mike Gold is their chief growth officer.
We are power constrained on the moon. That is going to be one of the most difficult and critical issues. And Redwire right now is working with NASA on a program called LVSAT with Astroscale. It's the Lunar Vertical Solar Array technology. And this goes back to AROSAs, that not only do they roll out, but they retract. And on the moon, one of the greatest enemies is regolith, is dirt. And when you get an array coated with regolith, it's obviously problematic. But if you roll it back, roll it out, you can shake off that dirt. So not only do we have a great system in terms of packaging, again, the roses roll up and then roll out get a lot more energy, but you actually have a terrific way to mitigate that regolith issue.
So that talks to what you were talking about before, about having a way to get those solar panels into place and the mass to power ratios that are required to get those things there. But the other thing was the project they're working on to build very large arrays of solar panels on the lunar surface to kind of try and generate the amount of electricity that might be needed. I still think that the nuclear is a better answer for that, because it just the density of what's required to get there and run it is less than it might be to generate the same power as the solar panels would.
The big problem with nuclear is, do we have a source in space? Because right now we have to take nuclear material from Earth.
Yeah, all the fissionable material has to go.
Yep, and it's got to go, then you launch it into space. And let's face it, if it's too enriched and there's too much of it, it's not really a spacecraft anymore. It's an intercontinental ballistic missile. And of course, people don't want plutonium falling on their heads or something like that.
In case there's an incident.
Yeah, exactly. And now, obviously, when you put nuclear power in space, it's not done to nuclear weapons standards or anything like that. Right. But what happens when we do need that kind of power density? You get out to Mars. What if you're out at looking at asteroids, trying to mine asteroids? And I still contend everybody's always goes into la la land about asteroid mining, and it's like, oh, look at all this rich minerals we could have out there. Okay, great. Now you're not going to bring the entire asteroid back, right? Because 98% of that is stuff you don't need. And if it's stuff you don't need, you cannot afford the fuel to bring it back. So you have to refine it in place, and you have to bring back at least a crudely refined product back, and then it's affordable. And so if that's the case, you're going to need energy density out in the asteroid belt for mining. Nuclear is probably your answer for that. So are there nuclear materials in space? Undoubtedly, but so far, all we really know is planet Earth has got it, and there's really not a lot of it on planet Earth. Right. We find it, we concentrate it, and it's a lot in human terms, but in actual terms for usage for large space operations over decades and decades, maybe not so much.
And again, space is a big camping trip. If you don't take it with you,
it is.
You're out of luck. And of course, then we start looking at the concepts of fusion versus fission. Fission is what we're all used to. Fusion is what the sun is. It's a much more efficient reaction to be able to generate power, and yet you've got to basically create a tiny little sun to make fusion work properly.
Yep, and we know we can create fusion. We've done it. We've done that with thermonuclear weapons. It's the difference between an atom bomb and a thermonuclear bomb. Is the thermonuclear bomb is fusion. It's fission that creates fusion.
Right.
And we've certainly created that. We just haven't controlled it. and that's what this whole idea behind the National Ignition Facility up in where is that? Lawrence Livermore Lab, I believe. It's up in the Bay Area. That's what they're trying to do with laser pulses. That we have ITER in France, which is a consortium most of the major players, countries on planet Earth, trying to get sustained fusion using a technology called tokamak. And then they have a funky type of tokamak called stellarators. Some companies are trying that, where they twist up the magnetic fields that confine the plasma that's used in these fusion reactors. And then there's Helion systems, or Helion energy, and I'm not quite sure how their thing work. I've seen some video on it, and they certainly seem to have an interesting way of going about it. And if they come about it, it's a pretty compact way of doing things. But I'm going to get this completely wrong, but I'll take a stab anyway. It's almost like they have two little tokamaks, or two little accelerators on the end of on each on the end of a, say, a vacuum pipe, I guess is the best way to put it. And both of them, you charge these things up with all this plasma, and then you release them going towards each other at the same time, and they meet in the middle. And when they do, they have all this energy. And when they meet in the middle, it's just like a collision of two semi-trucks. But much bigger and much more energy, and if the energy gets to the right amount, you can cause fusion. It looks interesting if they can make it work. This would be a fairly compact fusion reactor, but as far as I know, they have not gotten that to work yet. I could be wrong, but. It's an interesting idea. So we'll see. Fusion's one of those technologies they keep saying, it's we're going to have fusion technology in the next 30 years, and they've been saying that for the last 50. Are they going to get there someday? Yeah, I do believe they're going to get there someday. And is it going to be worth it? Yes, it will. It's one of those things where when you look at I saw a diagram about how it was like 1,000 cars of coal, rail cars of coal is equivalent to a kilogram of uranium or something in a nuclear power plant. And then that kilogram of uranium is some little microgram of helium-3 or something. I forget the comparison, but the amount of energy for the amount of mass that's going into it is just phenomenal. And the energy that you can theoretically get out of it we know from thermonuclear weapons, the energy you get out of it is quite phenomenal for the amount of mass that you put into it. So it could, if we can ever master it, it will be the future for energy, and at least until we come up with some new physics.
Until those antimatter reactors come online.
Yeah, exactly. Yeah, with dilithium crystals and,
Yeah. Well, we're just about out of time, Mike, but we want to talk a little bit about kind of what's in the road ahead, because it's pretty good possibility that we'll have a permanent presence at least on the moon in the next 20 years. If Elon Musk has anything to say about it, Mars may be in that mix as well. And all of that is going to require a lot of power in space. Now, one of the big issues on that is not only the sustainability, but it's collaboration. And I would posit that in that as well, there's going to have to be a lot of regulation that goes along with that, because as we talk about the developments in particularly like nuclear fusion, governments are going to have to regulate how all of that research is done on Earth before it can ever go into space. And so there's going to be some issues along those lines as well. So there's a lot that has to happen before a lot of these things come into fruition.
I agree. There's going to be a lot of government involvement and probably a lot of regulation on the Earth end. I kind of think history is going to repeat as we get into space. We're already seeing it a little bit with SpaceX and the FAA. Yeah. I think once you're off planet Earth, despite our treaties, despite all the agreements, folks are going to kind of do what they're going to do. And I think you're going to see that there's going to be some I think there's going to be some pretty risky and wild attempts at things in space. And if it's far enough away from the planet, I think most people are going to say, who cares? In other words, it's if you want to go out and blow yourself up out in some intermediary orbit that nobody goes through, and the likelihood of a spacecraft ever hitting anything out there is astronomically low. Who cares? Go run your experiment. The problem is going to be, are you near real estate?
Yeah.
In other words, if it's on Mars, people are going to care. Is it on the moon? People are going to care. If it's on Earth, we're really going to care. But if you're out in open space and you want to run some wild experiments, I think that's sort of the future of laboratory work, I think, because if in the end the experiment goes wrong, it's either stays there forever, or hopefully you have a safety device that basically is a retro rocket that lets it just dive into the sun. And it doesn't matter what kind of monster you create. It burns up in that big ball of fusion gas that we call the sun. But it's going to be interesting as we head out, and we've talked about power generation. We've talked about power transmission. There's also power longevity at deep space missions. How long can a battery last? You look at the radioisotope thermal generators for the Voyagers. They've lasted since the 70s now. What is that? Over 40 years, right? We're talking 50. We're coming up on 50 years. In when did they launch? 76, 77, I guess. I think it was 77 when they launched. So we're coming up on almost half a century on those things. And but how long will they last? And I know people like Arc and Light had been working on some really long-term nuclear type of batteries. Not a lot of power density. But longevity, oh, you betcha.
Yeah, and actually, we talked with Morgan Bordner, who was at the time the CEO of Arc and Light, who talked a little bit about that technology.
And when it comes to mining or colonization or any other mission where humans are going to be in space, it may be low power, but if diamond material can be fabricated in space, and you're not having to lift these things on a platform, right? So if you can lift the capacity to fabricate in space and then fabricate, these radiovoltaic and thermoelectric combinations, these distributed power management combinations, they may generate a modest amount of power, but when you live someplace that's that hazardous, or you're staying for long periods of time, you want reliability. And if there is anything wrong with your power systems, you can have a backup which is always on and uninterruptible. It's not chemical. It's not reliant on outside inputs. It's stable and consistent for very long periods of time. That may be a real winner. After all, that may be the key differential between survival and failure. So that's what we're kind of looking at. That's the problem we want to solve, is how to build in additional safety features for lower cost for us as a species as we go out into space.
And that's really a good point, because in space, it's not like we've got. I live in Florida. We've got a hurricane brewing off the coast right now. It's not, fortunately, doesn't look like it's going to come to my area. But for the people whose power goes off, then they just have to sit there and swelter without their air conditioning for a few days until it gets restored. It's an inconvenience, and sometimes a really big inconvenience, but it's not. In most cases, it's not life or death. In space, that's a much, much different equation.
Oh yeah. That's true, and inconvenience in space is much more than an inconvenience.
Houston, we've had a problem.
Yeah, we have.
Well, really, when we look into the future, Mike, obviously there's got a lot of innovation that has to be done in the realm of space power systems, but it does look like, from what we've been able to see and talking with people and all of the information that comes to us here at Ex Terra, it looks like that while a lot of these problems have not been solved and the solutions may be still years or decades to come, they're being worked on. And there are really very smart people who are working on these issues, and they will be solved eventually.
Yes, and there is a lot happening in this realm. And I guess my take on this is to those who are listening to this and those who read
you made it all the way to the end here.
And those who will read the article that we'll be publishing pretty much coincident with the podcast. Question is, do you want to see more of this? Because we're finding there's a lot more to this and a lot of different avenues, a lot of different aspects. It's quite a subject, particularly because so many different missions are being planned, whether they're space habitats, new space stations, going to Mars, asteroid mining, new different deep space satellites, just exploration of the moons of Jupiter or Saturn or Neptune or or even getting out into the Kuiper Belt and looking around, as well as the more of the Earth observation and communication satellites. The power story in space is a big one, and it's getting much, much bigger. Would you like to know more about it? Would you like to know more detail? Who are the players? What's happening? If so, let us know. Let us know. And because we're having fun researching what we're researching right now, and it's pretty awesome. And we've had a great time talking with the people in the industry that we've talked to so far, and we want to talk to more. So
if you have any suggestions about companies that we should be talking to, or people that we should be talking to, or if you know about a really innovative kind of power solution that we've not discussed, please let us know about that as well, because we're always looking for those kinds of leads, and we'll follow up on them. But as we said at the outset, everything works better with power. You need to have that ON/OFF switch in the ON position, and it needs to be having current running through it in one way or the other. So power in space is going to be, it's not something that's going to go away.
That is true. That is true.
And on that, we'll say thank you for listening. We're really glad you joined us. If you enjoyed the podcast, let us know in the comments. And of course, be sure to leave a rating and review, as they say on so many of these things. But let us know what you think and what topics you'd like to hear discussed on Ex Terra Extra. Until next time, I'm Tom Patton.
I'm Mike Turner.
Thanks again for joining us.